Greetings and hello, thanks for swinging by. This is a little video to show you where this formula that's used in introductory physics, the centripetal acceleration for circular motion is the instantaneous speed squared divided by the radius. My name is Haggis Henderson and I'd like to take you through this. Alrighty, this formula here gives the centripetal acceleration in meters per second squared for an object travelling in a circle. So here's a circle, here's a thing with an instantaneous velocity. V and, or if you like, a speed, and the radius is r. Now, I'm going to look at a short period of time. The velocity changes continuously, but I'm going to look at a short period of time so I can compare before and after and get a mathematical, a pair of mathematical points. Now, the reason the speed despite the speed being constant, the velocity changes is because velocity is speed and direction. The direction changes, so therefore we're going to have an acceleration. There's the radius, there's the initial velocity. Here's the final velocity. We need to look at the change in velocity because acceleration is change in velocity over time, divided by change in time. Now, we look at bits of geometry. There are two radii linking these velocity points. Give us a nice right angle here, which also means that the angle between these two velocities is also equal to the angle between these two radii. Now, the change in velocity is the afters minus the befores, final minus initial. We cannot subtract vectors, so we don't. This is the initial velocity, which is up and to the left. What we do is we add the negative of the initial velocity, which is up and to the left, and the negative of that is down and to the right. It's just the direct opposite. So now we can add them. So we can add them. There's the initial final velocity. Add on the negative of the initial velocity, and we get the change in velocity is pointing towards the center of the circle, which is fortunate because that's where things accelerate in, and the change in velocity should be in the same direction as the acceleration. If we come back to this bit of geometry here, there's the initial velocity there. What we can look at here is both of them have the same. There we've got two situations here. We've got an angle in here and an angle in here are the same. And the distance covered, d, which I've highlighted around the outside, for small angles, even though I've shown a big one, for small angles and small periods of time in between, that little distance becomes very close to a straight line, which is very useful. I'm going to consider it to be a straight line, even though my picture doesn't show that, because it's very difficult to draw that. When this happens, we get two similar triangles. We get two isosceles triangles. Come back a little bit. We've got two equal length sides here and the two equal length sides here, the two radii and the two velocities. Same angle, theta at the top, and the distance along the short leg is related to them both. So what we can do is we can have here, by similar triangles, the change in velocity divided by one of the velocities, one of the speeds, is equal to this distance around here divided by the radius. Because of the nature of similar triangles, the ratio of the side lengths is the same in all cases. And now we know that the distance travelled is equal to the speed times the time. So we can write that in there, or velocity times time, so we can get where we have d, we can put speed times time. And we can then, left-hand side's the same, the right-hand side where it had d has v times delta t. Then we can divide both sides by delta t, which we can do because delta t is non-zero. And we finish up with the left-hand side being delta v divided by velocity times the change in time, or speed times the time. And the right-hand side is simplified just v upon r. Then we multiply both sides by v, and we get delta v upon delta t, which is promising, as v squared upon r. That's also promising. But we also know that the change in velocity divided by the change in time is the centripetal acceleration. And that's what we're looking for. So the centripetal acceleration is equal to the square of the velocity divided by the radius. I hope that's useful to you. I'd be delighted if it is, and if it isn't, well, that's okay. But thanks very much for swinging by. I appreciate having you here.